Hi, this is Rashid from Colorado Chip Design. It's been a while since I recorded a video, so yeah, I was busy in a few things. Anyway, we were talking about ALU. So let's get started and finish ALU today. A little bit higher level. I know I started higher level, and my entire goal is, and the reason I'm giving all the background is people understand why we are getting into ALU, why we are looking into CPU. So it's important people, students have a higher level picture of it. Okay, so few things on, I won't bore you too much, but few things on higher level picture. So what we do is a programmer writes a C code. C code is converted into an intermediate format, which is called assembly code. C code is more higher level, like I should say a higher level code. I call it C code, like a C language. I already mentioned here. It's a higher level. You are not very specific. You will see in a minute how assembly is and why it's better than 0 and 1, but it's a very low level. Anyway, it's converted into assembly code, and then assembly code is converted into machine code, which is 10101, and that 10101, all binary things are stored in the memory. Okay, CPU's job is to fetch these instructions from the memory and then decode them, figure out what it is. It's like an add, it's subtract, it's and, it's whatever else is. And ALU job is to do that action, have the results available, and then CPU job is to write them back, let's say, in the memory. Then the tools that convert a C language or higher level language code into all the way to binary is called compiler. And the tool, if you are writing a very specific, very optimized code in assembly, then you use assembler to convert it into binary code. All right, so hopefully that higher level picture is clear. Let's look at an example. And this first example is of a logical instruction. So ALU stands for arithmetic and logical unit. So it performs arithmetic and logical operations. So example of a logical operation. You might be wondering what does and or those things do. So take a look at this example. In this one here, we have sensor 1 mask defined to be, this binary is 1, 0, 1. Then this is like a hexadecimal, it's X there. This is 2, so this is the binary, like 1, 2, 3, 4, 5, 6, 7, 8 bit. This is 4, so that is 4. So we have defined these variables in the memory. So that data is stored, and this corresponds to the location or the content of a memory location. Just think of it like that. Then in the main section of the program in C, I'm not giving an overview of C language, but these are simple things that you can understand. This is an unsigned number, 5. Decimal is 5 too. Now what you're checking is, like, these are the sensor mask we defined, and this is a status register. And what we say is, when status register is and sensor 1 mask, I mean this one is like same as this one. There's another way of saying it. I mean this whole thing becomes 1 when this and this are same, because they ended together. Then sensor 1 is active, else sensor 1 is inactive. Then a status register and sensor 2 mask, similarly this and this. So this kind of AND way of comparing these two. Okay, so what AND means, if you have 101 in one and 101 in another one, what you're ANDing is, you kind of ANDing them bit by bit. this one, 1 1, this one 0 0, this one 1 1. So you can see that for this one and this one, if one of them is opposite, output will be 0, right? Similarly, if this one is 0, this one 0, when both are 0, output is 0. So AND is a way to check to compare the two values. Hopefully that is clear. Do an example and you will understand that. If you don't, please comment or send me a text on LinkedIn. In case I can make a mistake too, because when you are actually teaching, it's always different. But this AND is in assembly language something like this. Now assembly language is very is specific to a particular instruction set. Like if it's an Intel x86, it will have a certain syntax for assembly instruction. If it's MIPS, if it's ARM, each one has a specific assembly level instruction format. So this is, I think, MIPS. So and you have two values stored in two registers. So CPU has brought these values into registers within CPU, and job of ALU is to AND them and put the results in this register. So that is where a logical operation is happening. Another example, but this time is arithmetic operations. So look at, this is a C code, main starts, and programmer has defined 4 variables, but 3 variables are given a value. So far in the course that I'm teaching here, we have studied about signed and unsigned integers, but we haven't looked into float. Float means you have a decimal, you have fractions there. How are you going to represent that? So I think I'm going to do a separate video after ALU on that, just a little bit higher level, how you can store digitally that type of data. So, but it's a floating point, not a fixed point. So what you do is you define them at float, right? So these 3 variables defined, and later what you do is your total cost is item 1 plus item 2 plus item 3. So here in a high level language, you are adding 3 variables. So ALU job is to add them together. And you will see that this high level code, and this is like an assembly in MIPS architecture, which is a RISC architecture. It's the same thing for this one. So MIPS is a simple reduced instruction set, not very complex, a lot of instructions like Intel x86. So it's called RISC. So here you look at eventually what the point of interest of what I'm showing you. It is doing to add. It's going to add this one, this one. The result comes will be added to this one. And those are this add and this add. And what it's doing is through registers. So a CPU's job is to bring those variables into registers, and ALU does is it just adds them and puts the output into another register. Okay, so you can see that eventually when compiler converts this into 1010 like a machine code, that is stored in the memory, and from where CPU job is bring them one by one, and eventually ask ALU to execute it. So this is an example of arithmetic. So let's get into our ALU design, which will be a combination of some of the operations that we did earlier on in all the videos so far. And my goal is just to combine and give you an idea. It's pretty simple. All you're doing is combining different things into a one unit, and you need to use multiplexer type of things. You need to make it generic, that ALU generic enough so that it can execute these instructions. And these instructions we wrote in assembly language. It's my own assembly language right now. I don't think this syntax follows any MIPS or anything. I just made a simple assembly language so that you can understand what I mean here. And for exactly that, we create an ALU. I mentioned here that assembly is always instruction set architecture specific, ISA specific. So the six instruction we have are add A and B, subtract A and B, check if A is equal to B, check if A is less than B, do an A and B and A and B are. Let's understand it with just one bit ALU. Now you have heard it's a 16-bit CPU, 32-bit CPU, 64-bit CPU. In those cases, these operations are on large number of bits. Let's say it's a 32-bit, MIPS 32-bit. So then your A is 32-bit, your B is 32-bit. In those cases, the entire ALU is actually performing operation on two 32-bit numbers. But let's do gradually to that stage. We will not go to 32-bit because it's hard to sketch that on here, but we will do maybe 4-bit. So 1-bit ALU. So just assume that our input data is stored in registers which are used to hold the value. And we will talk about those in the sequential videos. So A has and B, A is a register, B is a register. Then first thing, let's take one thing at a time. Now I have drawn this, you might see, and hopefully it's not overwhelming. But typically I draw this ahead of time so that my video passes a bit quicker. So add. Let's ignore everything. I think I can make a copy. Anyway. Look, ideally, let me draw it here. Yeah, I think that's good. So, and then, oops, that is not good. Let's go with blue. So this is my 1-bit adder. So I bring A and I bring B, which are 1-bit here, and I have output 1-bit. Now let's say I want to implement this instruction subtract. What do we do? Let's change the color. What we need is, if you remember, A minus B means A plus 2's complement of B, which means A plus 1's complement of B plus 1. So what we need here is that adder. I mean, we learned this in subtractor, right? Which A and you B. So B is inverted, which is 1's complement. Sorry, you probably be hearing this noise. And then you have 1 here. And the output is, result is subtractor output. Now what if you have to combine these two guys together? Now we have only one adder, and now let's use it adder or subtractor. And we have already done it, so it shouldn't be a new thing. If not, go back and look into subtractor topic, and that will explain this. So what you do is, what you do is you can, you put a multiplexer. Multiplexer is super important. Why we want multiplexer? Because for adder case is just as is, but in subtractor case we want to invert this. Okay, and also in the subtractor case we want to make 1. In adder case it will be 0. I mean, can be 1, but in subtractor case so a multiplexer, a favorite component, and that we call it's a select pin. When select is 1, we have this thing goes. When it's 0, when this thing goes. And once it's 1, we select this. When it's 1, it's also 1 comes here. So the whole thing acts as a subtractor. Now, so we had 1 unit with this one green kind of adder, and then the purple we added to as a subtractor. Let's add. Hold on to equivalent less than, do an AND and OR. So AND is this. So we bring A, wire it, then B, this pink wiring, pink here, output here. Now ALU output, keep in mind we can use for both subtractor adder just one input, but now if we get another input coming through AND gate, now output we have to send only one at a time because there's only one ALU. So another place for our multiplexer, you say, okay, we need to select here, we call it MS. Okay, we can give different values to, if we can give a 0 or 1, but if we're adding more things, 0 and 1 not sufficient, we need to make this 2-bit, so 0, 0, 0, something like this that I have done here. Since I'm gonna add OR here, I already said 0, 0 when MS, so my select means 0, 0 means you take this adder, 0, 1 this, and 1, 0 or the same thing, you bring A and B here and you select that. Now if I have to do AND, so this one is, I think I should say this one is MAS. So this bit is S, this ones are MS. So you can say that when select is 0, okay, select is 0 mean this comes here, and MS, sorry, not MAS, MS. MS comes here and we say 0, 0. So this, like when a combination of these three is 0, 0, 0, then we have A plus B at the ALU output. Or in other ways, we can say this is our OP code. When OP code is 0, 0, 0, we have A plus B. When OP code is 1, 0, 0, it's A minus B, because now you are selecting this path and bringing 1. When OP code is S, doesn't matter. Doesn't matter what you select here, because I'm going to select this branch. So you can see X, 0, 1. I mean, don't care. I think we also studied that thing X. So when it's 0, 1, select and 1, 0, we select OR. Got it? So far we have covered 1, 2, 3, 4 instructions, 2 instructions left. Hopefully that is clear. Okay, what am I doing here? I'm going into 4-bit now. So this is 1 bit, and I'm going for less than or equal to, because if both numbers are 1 and 0, then it's become a very simple thing, right? 1 and 0. But I just want to make a little bit bigger number so that comparison makes a little bit more sense. So let's see, this is 4-bit, this is 4-bit. So ignore, just ignore this area for a moment, please. So think of this is our adder, and adder or subtractor depending upon what you select through S and MS. That inversion and that select thing carry in is now part of this thing. Okay, that what I drew here, that's actually a good thing for me to say that. That entire this thing now till here, I am representing it as this. I shouldn't call it plus minus. Maybe I should call it 1-bit ALU, because it had logical instruction in it too. Okay, so I shouldn't call it. These are 1-bit ALU now. One bit ALU. So I'm going next level up. Not going in the details of all. I'm saying if my opcode is this, you will have A plus B minus B, or A and or B. And these greens are the inputs coming here. I told you what I've drawn here. Now A equal B. How you determine A and B? If A if A equal B, then what happens is we subtract A and B. Or in other words, the opcode we select first is such that we do a subtraction here. Because A minus B, if they're equal, the answer should be 0. Alright? So what I'm doing is, this might again be, I think we look at the how to compare numbers. And if I bring this one into a NOR, so think of if it's an OR, one of the input is 1, it output becomes 1. But putting NOR means, okay, sorry, if all the inputs are 0 or 4 bits, then OR will have 0, and you put an inverter and becomes 1. So we put NOR there. So what we say that whenever this guy is equal to 1 means the two numbers are equal. So this is kind of a check equality. It doesn't need this thing. It just uses as intermediate for this one. So this selection is such that we actually use the numbers here, but A equal B, instead of we'll be using this flag as opposed to the sum. So we need to have a control circle later on that checks this thing and it doesn't check the sum bit. Similarly, now A less than B, like this instruction. How do we check that? Now we already did that when A minus B. If now you need to look back into overflow. Okay, we're checking overflow, and if basically A minus B, if the result is negative, actually we're not checking overflow right now, sorry for that. So we're checking if like -3, if is A is a B and the result is negative, right? That means A is less than B. So what we have to figure out is the result. This, and we are expecting this as a sign number. This bit, the most significant bit, is going to be 1. If it's 1, which I took here, that means is true. A is less than B. If this becomes 0, that means A is greater than B. So if A is 3, 2 minus 3, you have +1. So that's where this is key. But I was mentioning we need to check overflow, because whenever addition subtraction happens, we need to ensure that there's no overflow, so that our result is not incorrect. We can reliably check that. And for that, this is the overflow logic. Again, I explained already overflow, so I'm not getting into that one. Go back and check my video on overflow. Those will be short videos, and you will understand what is the reason for this circuit and what exactly I'm checking. So in this exclusive NOR, I am bringing this most significant bit, and I'm checking this, which I said at that time is a B prime, because it checks just before the output of the mux inside for subtractor. That's what I'm checking here. And then the final. Again, all the details are there. If I repeat this, will made the video pretty long, and the whole idea was to explain all those things ahead of you. And here how we are combining that. So output of that will indicate if it's an overflow or not. It will be 1 if it's an overflow, if it's 0 is not overflow. This less than 1 means A is less than B. This one means A and B are equal. So we have combined a hardware now, and that's really the whole concept here. How you can combine all this into one unit, and it has outputs that can indicate different things. And then we will have a control logic, which we will study at some point later on, how you can gather these things and make some decision based on the instruction. All right, this was that overflow slide. I think that's it. Hopefully I have explained better. If not, please send me comments so that I can improve things. I try my best, but I don't know. You are the best judge. So thanks so much. Have a wonderful day or night. See you next time. Bye.